yesterday because it was just the same as our sine of alpha minus beta, where alpha is 3, beta is 1.2. So we have sine of 1.8. So we're just simplifying it to a single trig expression. Now the next one, sine of 2x cosine of x plus cosine of 2x sine of x. Since we have this, we're looking at one of our trigonometric functions. Now out of all of them, the most closely we're looking at is sum and difference, because we do have sine, cosine, cosine, sine. We're not looking at a cosine sum or difference, because one of the big things with cosine sum and difference is that cosines are together, sines are together. Since we have that alteration, we're looking at sine. Does that kind of make sense? Because cosines, well, actually, I do have it on slide 1. Because cosine of u plus v, cosine, cosine, sine, sine. Cosine minus v, cosine, cosine, sine, sine. With sine, sine, cosine, sine, cosine, cosine, sine, they actually have them mixed. And tangent in both cases is just straight up tangent the whole way through. Now, I'm not expecting you to memorize these, and it took me a while to actually see that kind of pattern, but also for sine sum formula, the sign between them is plus. Sine difference, sign between them is minus. Cosine sum, in between them is minus, sine difference plus. And that's kind of the way I've more or less memorized them, but you don't have to. You have a sheet, and after the semester, you probably won't ever use these again. So, not a whole lot of reason for you to go through the process of memorizing these. But we would match them up, because we see that I have sine cosine plus cosine sine. So we're looking at sine of alpha plus beta is the formula this matches to, because we have sine of alpha cosine beta plus cosine alpha sine beta. Our alpha is going to be 2x, our beta is x, and if we simplify this, we get sine of 3x. And that's it. We're just turning it into one expression. We can do the same thing with tangent. Well, part of the reason I know that this is tangent is because the whole thing just screams tangent. Now, the main places we look to determine if it is tangent of alpha plus beta or alpha minus beta is in the signs. If we go back up here, tangent of u plus v alpha plus beta plus minus. For our subtraction, minus plus. If it's addition, we have addition on top. If it's subtraction, we have subtraction on top. So we have subtraction on top, so it's our subtraction 1. But again, like I said for the last ones, all we need to do is just compare it to the general forms that we have. To get that there. Now for us, alpha is 1.1. Don't need that second parenthesis. Beta is 4.6. This will give us a negative angle, but that's fine, because it'll tell us it's negative 3.5. So that's it. Are you ready for this here? Okay. Now these here find the value of sine of u plus v. We will need our identity formulas, our reference page for some of this, but we're going back to triangles. Everything revolves around triangles. Triangles are the building blocks of most things, literally and metaphorically. Because when we look at this here, it does give us some information. Now, our sine of u plus v, if we look this up in the reference sheet, this converts to sine of u cosine of v plus cosine of u sine of v. This is just the straight formula. And to solve this, we need to find out what the value of sine of u, cosine u, sine of v, cosine of v is. Now, they were kind of nice. They told us cosine of v is negative 12/13. So I'm given that piece of information. I'm also told that sine of u is 4/5. I have half the formula already, but I don't have the other half. But it's not because I wasn't given it, I just haven't found it yet. Because with our cosine of v being negative 12/13, we know that the value of v, the angle, is between pi over 2 and pi. That's over here in quadrant 2, is where v is located. Let's get this color. This is where v is at. Okay. Now, u is between 0 and pi over 2. So u is over here in quadrant 1. We're good with everything so far. Now for v, I'm going to draw a triangle. It is a right triangle, but I'm going to draw a triangle over here. Size really doesn't matter for this here because it is a triangle. We're going to put numbers. We're not going to make this to scale. Otherwise, it would be kind of challenging to make it both of them be to scale. We just need the triangle. And the other piece of information with this triangle is they told us cosine of v is negative 12/13. Cosine is adjacent over the hypotenuse. We know the negative has to go with the 12 because we're on the negative x-axis. And also the hypotenuse is never negative. So we get this here. Our other triangle is in the first quadrant. I'll draw another triangle. And this one here, they told us sine of u is 4/5. Sine is opposite over the hypotenuse. Sine, the 4 is positive because we're on the positive y-axis. Hypotenuse has to be positive, so they're both positive, and we get this here. Now, out of the two of these here, our one with u, I have a feeling you know what the third side is. Three, because it is a 3, 4, 5 right triangle. You know what the other side for the other triangle is? If not, that's fine. It's not one of the more known. Well, it is and isn't. It's not. ACT doesn't use it as often. They do sometimes. But even so, we can still use Pythagorean theorem. It doesn't matter what we define as A or B, as long as we pick negative 12 as A or B. It has to be just one of them. B is going to be the other term. The hypotenuse is 13, and we could do this in one of two ways. I can continue solving it as with squares and go from there. Because what we could say is I'm just going to minus negative 12 squared from both sides, telling me b squared is equal to 13 squared minus negative 12 squared, square root both sides, and just plug that in. And grab a calculator, say second square root, 13 squared minus negative 12 squared, giving me 5. And that works. B is 5. Now the other option, if you erase all this here, is that I go on and square it. Square 12 squared, 13 squared, minus the 144, telling me that b squared is 25, square root both sides, b is 5. Now we technically do have the plus or minus when we take square root of both sides, but because we're in quadrant 2, we're looking for the y side of the triangle, and we're in the positive y-axis, it has to be positive. Questions on this here? Now, the reason we go about doing this is this actually gives us a lot of information, because what we're missing for this is cosine of u and sine of v. Well, cosine of u, I'll write it down here. Cosine of angle u, so over here, is adjacent over hypotenuse. Well, from the beginning, we knew the hypotenuse was 5. Now we know the adjacent side, which is 3. So cosine of u is 3/5. We're also missing sine of v, which is opposite over the hypotenuse. Well, the hypotenuse is 13. However, the opposite side, which we didn't know that we now do, is 5. Question how we found this here. Now at this point, we could type this entire thing into the calculator, as we have it here. If we did this by hand, we'd multiply these together. 4 times negative 12 is negative 48. 5 times 13 is 65. Plus. Now I'm going to ignore the fact that we do have a 5 in the numerator and 5 in the denominator, because every bone in my mathematical body is saying we can cancel those out and simplify. But we're adding 2 fractions together, yes? So we have to leave these 5s alone, because 5 times 13 would give us 65. Because to be able to add or subtract 2 fractions, the denominators need to be the same. So if I did remove the 5 over 5, I'd have to put it back in to be able to actually add these two together. 3 times 15 is 15. The denominator will still be 65, but we have negative 33 over 65 as the final answer. Because here, because I could have said 4/5, parentheses, negative, yeah, it was 12/13 plus 3/5 times 5/13. Enter. Calculator did it at that point. We didn't have to go through the process of actually doing the multiplication and then simplifying. Calculator would have done it for us. Questions on this here? Well, find the information, find the value from the given information. So these are a little different. On the homework, luckily, they will give you more than one problem for a given setup. I think it's at least two, where you can do these here, set it up once, solve them with those given values, and go from there. You're not going to have to reset it up every time. But we're going to do a setup again, just so we can see how it's done. Now the first one tells us cosine of v is -3/5, where v is between pi over 2 and pi. So we're back over here. It's v. Cosine is adjacent over the hypotenuse. Luckily for us, they set cosine of u at between 0 and pi over 2. And they told us sine is 12 over 13, opposite over the hypotenuse. So we get this here. The reason I said luckily is because there are some problems where they put u and v in the same quadrant. And if that is the case, we have to set up two triangles so we're not overlapping information too much. Or sometimes they'll put them in the first and fourth, where they're kind of sharing a side, or second and third. In some of those cases, we have to either use different colors or set up two. Now, luckily for us, v, other side is 4. 3, 4, 5 right triangle. Since we're in the positive y-axis, it's positive 4. With u, two sides of our right triangle are 12 and 13. 13 is the hypotenuse. And we've just solved for the other side once today. It is 5. If you want to check that in a calculator, we can. Just 5 squared plus 12 squared, 169. 13 squared is indeed 169. So we have this here. Questions on this so far? Now, we need to find the value of this, cosine of u plus v. And if we look at our reference sheet, it's going to tell us that cosine of u plus v is the same as cosine of u times cosine of v minus sine of u sine of v. Cosine of u was not given to us, but if we look at u, the adjacent side is 5, the hypotenuse is 13, so cosine of u is 5/13. They did give us cosine of v as -3/5, so we did have that one. Sine of u was given to us as 12/13. Yes, but they didn't give us sine of v. Yes, okay. Now I went on and put 5 because with cosine of v, the hypotenuse was 5. We know the hypotenuse has to be 5. But the adjacent side, not adjacent, sorry, opposite side for sine would be 4. So we get this here. And again, at this point, we could plug the whole thing in. Let the calculator do it. I'm just going to do this by hand, because 5 times 13 in both cases is going to be 65. Our first 5 times -3 is -15. 12 times 4 is 48. This is going to be very, very close to 65, but it will not cross it. And it'll be 63. 2, yep. So we have negative 63 over 65. Now, I did say it would get very close but not cross it very confidently, because sine and cosine will never be greater than 1 or less than negative 1. Since this is negative, even negative or positive, 65 over 65 would be 1. If we went above it, it would be outside that range. And the only way it could be outside that range is if we were looking for, say, 2 cosine, then it's between 2 and negative 2. But it gives us an idea. Questions on this here? Right, is an algebraic expression. This is going to take 3 days. Cosine of arc tangent of 1 plus arc cosine of x. Well, we're going to be looking at triangles in 2 specific cases. Because first one I'm looking for is arctangent of 1. And the other is arc cosine of x. Because both of these equal an angle. I'm just going to call the first one alpha and the second one angle beta. Alpha and beta. Because alpha equals arctangent of 1 is really saying tangent of alpha is equal to 1. Which means it's pi over 4. That seems like an odd way that I can just jump there. Part of that's doing this for a while, but tangent only equals 1 if sine and cosine have the same values. Well, the only place that sine and cosine have the same values is pi over 4, or one of its multiples. Because it would be considered negative pi over 4 if we were looking at negative 1, but we get there in either case. Because this is a funny kind of problem. Yep. Yeah, so it is going to be that, but to work this out, we need a little more information than that. And they're going to do it based off of this triangle here, calling this alpha and beta. They use different ones because if you do look at the book for this, they call it U and V. But we have this here. And tangent of this angle equals 1 means the opposite and adjacent sides are the same. Because that's the only way we get it. Opposite and adjacent have to be the same. I could set it whatever I want because I could say it's 2 and 2, but 2 over 2 reduces to 1. So might as well let's leave it in a simpler form and say 1 and 1. To find the hypotenuse, c squared is equal to 1 squared plus 1 squared, or 1 plus 1. C squared is equal to 2. And if we take square root of both sides, c is just the square root of 2. Also, because we know that tangent is equal to 1 only at pi over 4, 45 degrees. It means the other angle has to be 45 degrees, which actually makes this a special right triangle, 45, 45, 90. If the two sides are 1, the other side's whatever that length is times square root of 2. A lot of information, but we could do this here to get there. So really, to get there, the key is that tangent's 1. 1 over 1. Opposite over adjacent. whenever we're given a value without a denominator, well, the denominator is understood to be 1, so we can use that, especially in these here. Oddly enough, I think this is the only case where knowing that, besides reciprocals, is actually useful. Here, we're saying cosine of beta is equal to x. And again, as we just said, the denominator is 1. So cosine of beta, we're saying the adjacent side is 1, or sorry, not 1. The adjacent side is x. The hypotenuse is 1. This is where it gets a little tricky. You have room. I've run out of room. Yes, so I would still put it somewhere over here, as long as you do have space underneath. I'm going to open a new page. Because in our triangle, 1x, we're trying to find the missing side. A squared plus b squared is equal to c squared. We can say a squared is our x. Don't know what b is, but c is 1. X squared simplifies to x squared. I still find that as a funny statement even now. 1 squared is 1. Now to get b by itself, we would subtract x squared from both sides. Telling us that b squared is equal to 1 minus x squared. And again, as before, to find its value, we take the square root of both sides. So b is equal to the square root of 1 minus x squared. So we get this here. Now, I know that you kind of have probably some vague memory in the back of your head that's kind of clicking why we're doing all this. But without having done this before, this makes no sense why we went through all that trouble to do the triangles, set those up, and get them the way they are. And it's because this here is our addition or our sum formula for cosine. And with it being a sum formula, try writing that again. Because our sum formula is cosine of alpha cosine beta minus sine alpha sine beta. This is the form that we have. And if I'd have plugged it in as we had to start with, it would have been cosine of arc tangent of 1 times cosine of arc cosine of x minus sine of arc cosine or arc tangent of 1 times sine of arc cosine of x. That's a messy thing in and of itself. We have way too much sine and cosine inverses, tangent inverse. There's too much. But I know that this here, this angle that we're really trying to find, because when we find arc tangent of 1, we find the angle, then we would plug that angle into both of these and find their corresponding values. Well, cosine of alpha, we know the alpha angle corresponds to this triangle here. Well, now I can just use that angle with cosine, because cosine is adjacent over the hypotenuse. So 1 over the square root of 2, and we will rationalize the denominators in a minute. We'll save that for later. Cosine of beta. Arc cosine of x was our beta, so we do have a triangle over here for beta. which is x over 1. Which if we applied the normal formula, cosine of arc cosine of x, gets us x over 1, which is just x. So that kind of worked out the way it should. Minus. Here's where some of it would have been a little tricky, especially because we'd have sine of arc tangent, cosine of arc tangent. Those don't simply cancel each other out. But I can come over here. And this here, sine opposite, which is 1, over hypotenuse, which is square root of 2. Again, we'll rationalize denominators later. Sine of beta, coming over here, and sine of arc cosine would not simply just cancel each other out. But sine is the opposite side, which is our square root of 1 minus x squared, over the hypotenuse, which is 1. Questions on how we got to this here? Now, unfortunately, unlike the rest of them, we have to do these by hand because we don't have the ability to plug x into either the 84s or the 30xs without it having a specific value. Now, our first one, 1 over the square root of 2 times x over 1, is just x over the square root of 2. Minus the second one, well, 1 minus x squared over the square root of 2, because we'd have 1 times the square root of 1 minus x squared, which just gives us 1 minus the square root of 1 minus x squared. And the square root of 2 times 1 is square root of 2. Now, since the denominators are the same, we can go on and subtract the numerators. But because they are not like terms, we have to leave it as is here. It's been a while since we've actually had to do this by hand, rationalizing the denominators. And the few times we've done this, I kind of just gave you the answer more or less. But to rationalize a denominator, we're going to multiply here, in this case, the square root of 2, by something that will make the radical go away. Well, to make it go away, it'd be nice if it was 2 squared, because the index is 2, so we need that to match. So we just multiply it with the square root of 2 to get those to match up. Because in the denominator, square root of 2 times the square root of 2, we can say it is one of two things. I'll put this as more of a side note, as the square root of 2 squared, or the square root of 2 squared. And if you're not watching the video, that sounds like I said the exact same thing. But in both cases, we get 2. Now the numerator, we need to multiply this through both of them. X times the square root of 2 is x square root of 2 minus, and if we multiply the square root of 2 by the square root of 1 minus x squared, incidentally enough, we can actually distribute the 2 through what's inside of it, which gives us 2 minus 2x squared. And if you're looking at the textbook version of the answer, the first part of it is a little different because they wrote it as the square root of 2 times x. I do not like having variables after the radical because it's very easy for it to wander its way back inside. The x is outside. If we did put the x inside the radical, it would be 2x squared inside. But we can pick this up tomorrow.